Very good morning. Today we discuss sampling distribution of parameter estimates for multiple linear regression. You have seen in last lecture that how we have estimated the parameters beta, and you have seen the estimated values are basically point estimate. We have discussed earlier that the estimates are basically random variable, and then they have probability distribution, which is called sampling distribution. So today you will see sampling distribution of beta. In the process you will learn what is expected value of beta cap, covariance of beta cap, then individual confidence interval for model parameters, as well as confidence region of beta. Let us see the next.
Our discussion is sampling distribution of regression coefficients. Okay. In last class we have estimated beta coefficient like this: x transpose x inverse x transpose y, where x is the design matrix, first column is all 1, second column will be the first variable data x11, x21, then xn1. Similarly, last one will be the pth variable data x1p, x2p, xnp, and y is the n observations. This is n cross 1, this is n into p plus 1, and this one beta, this will be definitely p cross 1, p plus 1, p plus 1 cross 1. So if you collect one sample, you get some value for beta cap. If you go for another sample, your beta cap will be different. For example, sample 1 beta cap may be 1, sample 2 beta cap maybe for sample 2. Like this, if you go for n sample, so beta cap n, so you will be getting series of beta values. And please keep in mind that beta is, or beta cap is p plus 1 cross 1 vector, that is beta 0 cap, beta 1 cap, like this, beta p cap. So beta cap is a random variable, and we want to know its distribution, and that is the sampling distribution of regression coefficient. And then using the distribution of beta cap, we will derive confidence interval and other things. So for a distribution, you require to know what will be the expected value of beta cap. We want distribution of this. So we first require to know the expected value of beta cap. This will be expected value of beta cap is x transpose x inverse x transpose y. So we can write this as expected value of x transpose x inverse x transpose. Now you all know y is x beta plus epsilon, as y equal to, this is the regression equation. So if we do little more manipulation, this will become x transpose x inverse x transpose x beta plus x transpose x inverse x transpose epsilon equal to, now x transpose x inverse x transpose x, the symmetric matrix inverse symmetric matrix, we will get it identity matrix I. So, this will become I. So, ultimately expected value of I into beta is beta plus, as x the data already collected. So, x transpose x inverse x transpose, this is the fixed quantity. So, we will keep it out from the expectation operator, then we are writing expected value of this. Now, expected value of beta is beta, because beta is the regression coefficients. These are regression parameters or coefficients from the population point of view, that is constant, plus expected value of error is 0, that is our assumption. So, you will get x transpose x inverse x transpose into 0. So, this will become beta. So, it says that expected value of beta cap is the beta, that is unbiased estimation. Okay. So, in addition, first we have taken this one, that expected value of what is the beta cap. We want to know also the covariance matrix of beta cap. So, we want to know covariance of beta cap. This will be expected value of, all of you know that beta cap minus expected value of beta cap whole, this is p cross 1, no, this into beta cap minus expected value of beta cap, this transpose, because covariance matrix of beta means it will be beta cap is a p plus 1 cross 1. So, our covariance matrix of beta cap, that will be a matrix of p plus 1 cross p plus 1. Okay. So, now we can write that this one expected value of, now beta cap minus expected value of beta cap is beta into beta cap minus beta transpose. Okay. So, let us find out what is the value of beta cap minus beta. Okay. So, what the value of beta cap, if you see here, when we have described this one for expected value, this one is this final, that means ultimately you got beta plus this quantity, this is beta plus this. So, I can write this one using this, that beta plus x transpose x inverse x transpose epsilon, that is we can write for beta cap minus beta, this beta is there. So, beta cancel out, what that means, this quantity becomes x transpose x inverse x transpose epsilon. Then beta cap minus beta, this transpose, this will become x transpose x inverse x transpose epsilon transpose. So, when you make transpose, it will be just the reverse order. So, epsilon transpose x transpose is x, and x transpose x inverse, that will remain, because symmetric matrix, that will remain this. So, epsilon transpose x transpose x inverse, as x transpose x is symmetric and definitely square also. Okay. So, then if we use this, if we use now this operator, expectation operator here, so we can take one more page. So, expected value of beta cap minus beta, beta cap minus beta transpose, this is nothing but expected value of, it is coming x transpose x inverse x transpose epsilon, then for this one epsilon transpose x x transpose x inverse, this is coming. So, for this we have written this portion, for the other one written this portion. Okay. Now, again what we will do then, we will just bring out the fixed values like x transpose x inverse x transpose, then expected value of epsilon epsilon transpose, then x x transpose x inverse. So, what is the this one expect covariance matrix of error term? Now, covariance matrix of error term we say that equality of variances across the x observations. So, that will for y and that will go to the error place. So, ultimately expected value of epsilon epsilon t, this will become sigma square into I, because there are n observations for a same, that is from the assumption it is coming. So, this quantity will become x transpose x inverse x transpose sigma square I x into x transpose x inverse. So, now sigma square is constant, I is the identity matrix that will go. So, finally, it will be like this x sigma square x transpose x inverse. Now, here is x transpose, here is one more x, then x transpose x inverse. Tanmay, okay. So, what is this quantity then? X transpose x inverse x transpose x, this is again I. So, sigma square I is sigma square. So, this will become sigma square x transpose x inverse. This is what is covariance of beta cap. Okay. So, then how do you get the value of sigma square? Sigma square is also not known. So, sigma square will be S E square, that means from the error whatever value you get, from there you will calculate the variance component, and this will be SSE by degrees of freedom for SSE is number minus parameters estimated. So, we can write then that covariance of beta cap is S E square x transpose x inverse. Okay. So, you will not get this sigma square value, these are population value. So, from simple error you will be able to calculate S E square. This S E square is nothing but SSE by n minus p minus 1, and this n minus p minus 1 is coming because there is n is the sample size, number of parameter to be estimated is p plus 1. So, this degrees of freedom is lost when you are calculating the errors. So, this is the case. Okay. Then we can say that beta cap is a random variable, with mean vector beta, and covariance matrix we can write this way sigma square x transpose x inverse, this is correct. What will be the distribution? Its distribution will be multivariate normal, this is the assumption. We have started with that data coming from multivariate normal, and the way you have estimated beta, beta cap is x transpose x inverse x transpose y. So, here what happened, because of this multivariate normality assumption, this will also become multivariate normal. Now, this multivariate normal, what will be the
We assume that data is coming from multivariate normal. So x and y both are multivariate normal. The assumptions.
So, in actually in regression the error is the key point, key issue. Y is definitely multivariate, y is here one variable, so normal. Actually what is happening here in this particular, in this regression, multiple regression case, so you have a different sets of x values, then you are calculating y values, and everywhere there is error. This error is if there are n data point, n error will be there. So, that error component also will go for multivariate n cross n. So, we are here we are estimating p plus 1 parameters. So, beta is, we are assuming that this is multivariate normal with p plus 1, and this is what is the distribution. Okay. This is the distribution of beta cap. Now, if this is the case, now we will go back to our some earlier lectures where we say if x, this is not one to one relation, but to get some clue for related to beta for some more derivation. We have seen that suppose x is multivariate normal with mu and sigma, then we calculated x bar, and that one is also multivariate normal mu and sigma by n. So, similarly, this we have taken this data from multivariate normal and we calculated some statistics. The x bar is all statistics, here also we calculated some statistics, and for that statistics we found out the mean vector and the covariance matrix, and like x bar covariance matrix and mean is also calculated. So, in the same manner it is beta is multivariate normal. Now, what happened, we have also described that what is the confidence region. Can you remember confidence region for mu, where mu equal to mu 1 mu 2 to mu p, that we have discussed earlier, and with the help of x bar we found out where x bar is x 1 bar, x 2 bar, like x p bar, we found out this confidence region of mu. And if you can remember, you will find out that we have found like this, that n x bar minus mu transpose S inverse x bar minus mu, this will become less than equal to n minus 1 p by n minus p f p n minus p, this one probability of this equal to 1 minus alpha. So, this is the confidence region we found out with respect to that population mean vector. So, can we not find out the similar thing here with respect to beta? Getting me? So, then it is not derivation, what I am giving you, it is not derivation, it is just understanding that why, how those confidence regions can also be calculated with respect to beta cap, which is multivariate normal. So, can we not write like this then, beta cap minus beta, that is x bar minus mu, similar type of things, this transpose, there was S inverse. So, S is the covariance matrix. So, our covariance matrix is what? Our covariance matrix is sigma square x transpose x inverse, which is we can write S square x transpose inverse. So, what do you want? Inverse of this, that means x transpose x by S square. So, if I write like this x transpose x, okay, I am not writing AC square here, later on we will write AC square, then beta cap minus beta. What distribution it will follow, that is important, that also follows here, that this show AC square it will come, again I am telling you it is not derivation. Derivation may be something, some different way people will come, but this is the way we will understand for our application. Okay. So, this is S E square P plus 1 F P plus 1 n minus P minus 1 alpha, probability that this quantity will be less than this is 1 minus alpha. So, this AC square what is coming out here by this we are keeping here, and rest of the things are like this, but there are some modification with respect to the parameter number of parameters to be estimated. So, this is the confidence region for beta, but we are not what we will do with the confidence region. So, parallelly then what you require to do? You require to go for simultaneous confidence interval. Understood, Tanmay? What I am saying, the beta cap is multivariate normal. Beta cap is a statistic. Earlier we have seen x bar multivariate normal, that was a statistics. With x bar we created the confidence region for mu. Here with beta cap we want to find out the confidence region for beta. So, this is the formulation which can be used. Then from confidence region we have gone to simultaneous confidence interval. For two variable case you have found out that when multivariate normality will be coming, that something like this you got confidence ellipse. So, from this ellipse to you want to go to the sides, what is this interval confidence, what will be this side, that is true for beta cap also. Suppose this is beta 1 cap and this side it is beta 2 cap, same thing, nature is same. Okay. So, for simultaneous confidence interval I think we have seen two approaches, one of them is Bonferroni approaches. So, this Bonferroni approach is easier for us and it gives good result also. So, we can use Bonferroni approach, and in regression whatever it is found that individual parameters when you test, and you will find out that interestingly this situation will arise, that if I go instead of beta cap, if I go for beta j cap, what will be the distribution of this? This will be univariate normal, one variable. So, this will be univariate normal. Okay. Now, depending on sample size what will happen? We will go for, when we have taken x bar, if you can remember, we created something like this, that x bar minus expected value of x bar divided by standard error of x bar. Can you remember? This one is nothing but x bar minus mu by s by root n when sigma is not known. So, this follows the distribution with n minus 1 degrees of freedom. Now, for beta cap let us do the similar thing, that if I write that beta j cap minus expected value of beta j cap divided by standard error of beta j cap, what will be this value? This value will be beta j cap minus beta divided by what will be the SC standard error of beta j cap, that you require to find out. How do you find out this one? See, you know that covariance structure of beta cap is already given to you. This one is nothing but AC square x transpose x inverse. So, if I write x transpose x inverse as C, then this is AC square into C. So, this can be written like this, that AC square will remain, then how many, what is the size? Size is P plus 1 cross p plus 1. First one is 0, then 1 like this up to p, here also 0, 1, so up to p. So, first one is C 0 0, then C 0 1 like this C 0 p, then C 0 1, C 1 1, C 1 p. So, then here it will be this is 2, so C 0 2, so like this C 0 p, then C 1 2 like this C 1 p. So, in this manner you will calculate, then C p p, somewhere the jth one will be C j j. Understood? So, what I am saying that X transpose X inverse is a square matrix of the order p plus 1 cross p plus 1, and that we are writing in terms of capital C, and each element is C j k. Now, j stands from 0 to p, k stands from 0 to p. So, the diagonal elements of this when multiplied by AC square will give you standard error of beta j. So, this will be S E square into C j j, and off diagonal will give you the covariance between the parameters estimates. Okay. So, you can write now that beta j cap minus beta by, you can write this AC square, this is standard error. Achha, now, as it is standard error, we have to give the square root. This is standard error, so we have to give the square root, and this component is the variance component of diagonal elements are variance. So, AC square C j j. Okay. Now, under the assumption of null hypothesis H 0, that beta H 0, our null hypothesis that there is no effect of the x j variable. Now, what do you mean? Our regression equation is like this: beta 0, beta 1 x 1, beta 2 x 2, dot 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 beta p x p plus epsilon. So, somewhere there is, suppose this is our beta j x j. What we are saying, if x j has no relation with y, other way x j does not contribute in explaining the variability of y, then we can assume that beta j value is 0. So, this is our null hypothesis when you test the individual regression parameters. Then alternative hypothesis is beta j not equal to 0. So, if we create this, what will happen ultimately, then under null hypothesis, this quantity, that beta j minus this will be 0, beta j equal to 0. So, then by square root of AC square C j j. Getting me? Difficult?
No, sir, beta j minus beta, there was.
Beta j cap minus beta j, all are beta j here, all are beta j. Beta j, because we are talking about the jth variable only. Okay. Now, I will come back to this estimate that test part later on. Now, let us see that we will just what we are developing that confidence interval part. So, beta j minus beta by square root of AC square C j j, this will follow T distribution with n minus p minus 1 degrees of freedom. Okay. So, if this is true, then we can write like this is my T distribution this is 0, this one is t n minus p minus 1 alpha by 2, this side is alpha by 2, this side also alpha by 2, this is minus t n minus 1 minus n minus p minus 1 alpha by 2, this value. And please remember that we are talking about beta j only. Under null hypothesis, this is acha. Null hypothesis case we will not discuss now. So then, can we not write down now with respect to this quantity will be beta j cap minus beta by root over s square c j j less than equal to t n minus p minus 1 alpha by 2, and here minus t n minus p minus 1 alpha by 2. Beta j. Okay. So now manipulate little more. So what you require to do then, you want beta j here, this side and this side less than equal to and less than equal to. This quantity will come here as beta j cap, okay, plus t n minus p minus 1 alpha by 2 into s square c j j, and this side it will be beta j cap minus t n minus p minus 1 alpha by 2 root over of s square c j j. This is from usual individual the t distribution, but again you see that it is n minus p minus 1 degrees of freedom is much less compared to n minus 1 in the original x bar case. So what we have discussed then so far, we have discussed ultimately we found out that expected value of beta cap, we found out covariance of beta cap, also we found out that individual confidence interval for beta j. Also you know now that what is the confidence region for beta with the help of beta cap, and from there using Bonferroni approach you can using you can use this equation. Only thing is that this will not be alpha by 2, it will be alpha by 2 into number of parameters p plus 1. Okay. So that means this will be beta j minus t p minus 1 alpha by 2 into p plus 1 square root of s square c j j less than equal to beta j less than equal to beta j cap plus t n minus p minus 1 alpha by 2 p plus 1 square root of s square c j j. Tomorrow if possible है